Okay, so let's get into part 2 from lesson 2. The part 2 is most common RAC tuning tips. And the first slide is giving you the list of common tips. And from second slide, we will get into some examples. And as you can see here, application tuning is often the most beneficial. Yes, whenever possible, make your application scalable and tune your application. And then it's a good idea to reduce the long full table scans in OLTP system. Okay, why? If you issue SQL statement that requires full table scan, then multi instances must be involved together to share messages. So to reduce block transfer or message transfer, it's a good idea to reduce the long full table scans, especially in OLTP environment. And also use automatic segment space management. And it gives you a node affinity feature, meaning that ASSM is used to manage block available for insert statement or update statement. So when you connect to instance 1, and it's possible to get the range of blocks that are assigned to only instance 1, and also when you insert from instance 2, then we can also leverage it in a range of blocks assigned to instance 2, so that way we can reduce block transfer in case of insert statement from multiple instances. And also, you can take advantage of a key derived from sequences, and especially when using sequence as a key, then it's a good idea to use a cache option. So by doing so, we can reduce block transfer, especially when using sequence, use a cache and no order option. So that way, when index key is required from each local instance, we can get a sequence value as an index key. So that way, we can minimize block transfer and message transfer. And also use partitioning to reduce inter-instance traffic as well. By default, when instance requests the resource, the ownership is evenly distributed by using internal algorithm. But over the time, it's possible to change the ownership of an entire object, so even at the partition level. So if you have a very huge table, and it's a good idea to partition it. So by doing so, we can assign ownership of each object to a specific instance. And also using partitioning, it may be a good idea. Also, if you expect a concurrent truncate operations, okay, that's what we're going to cover in the next few pages. And avoid unnecessary parsing, and also minimizing lock usage, and also remove unselective indexes as well. Think about that. You have actually a many number of unused indexes. We create index possibly to improve your query performance. But if you create indexes without knowing the actual usage of the index from your application, then it will slow down your DML operation. So if you have a very heavy insert statement or update statement, your index also must be updated, even though those indexes are not used by your application. Then there may be some contention area, okay? And also configure interconnect properly. So you can use a gigabit network, or 10 gigabit network, or InfiniBand network, or you can use a jumbo frame. So when you actually configure network, you will have to configure network interface and switch and all consistent. So that way, you can avoid the potential issue. And also you can employ in-memory parallel query as well, meaning that you can actually run parallel queries directly through SGA memory space instead of using PGA. So that will give you another nice benefit. So that's basic tuning tips. And based on that, we're going to get into a few examples. So here we have an example of an index block contention. And we have a couple of observations here. We have index contention and global cache buffer BG and block BG and split. And think about that. You have actually concurrent DMLs through multiple instances. Okay, then only table blocks will be transferred. But if you have a table with a many number of indexes and those are not selective, if that is the case, every time when you insert from multiple instances, then your index also must be the updated and transferred across multiple instances. Because of that reason, and you will see this kind of observation. You have a transaction index contention, global cache buffer VG, so meaning that same hot block accessed by multiple instances from multiple sessions from multiple instances, and also block BG before the commit, another instance requests the same block. Thus, the redo must be flushed. Okay, so there are actually many things going on. In order to resolve this problem, and there may be actually a few solutions. And if this is the result of unselective indexes, then identify unused indexes, make them invisible, test it, and drop unused indexes. But if these indexes are really used by your queries, then you may want to actually use hash function and hash partition to spread your index key across the leaf blocks. Okay, or you may want to use a reverse key index, but it can resolve index contention. However, you have some limitation of range scanning. Okay, or possibly if you can derive index key from the sequence, then you can take advantage of a sequence as well. For example, you can actually create a sequence, and there are 4 possible ways to create sequence: cache order option, cache no order, no cache no order, and no cache order. And the recommendation is, if you want to use a sequence to resolve index contention, then use a cache no order option, and then put the cache, the large enough sequence values in each instance, and then use it as index key. By doing so, we are able to spread the sequence value across the leaf blocks, and each instance only access to the range of blocks assigned to each instance. Okay, for example, we cache 50,000 sequence values, and the list of leaf blocks in the left-hand side will be accessed by instance 1 in this example, and also range of index blocks in the right-hand side will be accessed by instance 2. By doing so, it's possible to reduce index contention. However, if there's an instance crash, then you will have some gap. So in your environment, the order of an index key value is very important. Then you will have to use another option, no cache option. Okay? Another example is undo block considerations. So let's take a look at one review topic. And we had a discussion of undo table space. If you remember, it was in lesson 4. In lesson 4, we had this discussion. And if a session 1 issue update statement, then data block is cached in the buffer cache. And before update, before image of a data must be copied over to undo block. That's one thing what we have to do. And also, we can actually change it, the data from data block to new value. Okay? And then when you issue a select statement from time 2, then we're going to actually get this value as a returned value. From session 3, when issuing the select statement, then data must be from consistent reader block. So how do we create a consistent reader block? So the idea is basically we copy block that contains uncommitted transaction here. Okay, and then we apply undo to roll it back to A, and this is your consistent reader block. So your SQL statement from session 2, this will get value A from consistent reader block. This was one concept what we learned. Another concept what we learned was this. Okay, this is another concept. Another concept was if you have a multi-node RAC database, and we assign one undo table space to one instance. So if you have a 4-node cluster, 4-node RAC database, undo TBS1 will be assigned to ORCL1 in this example, and undo TBS2 will be assigned to ORCL2, and undo TBS3 will be assigned to ORCL3, undo TBS4 will be assigned to ORCL4. So we assign one undo table space to each instance. That's our concept. Now suppose that you have a table with a few set of indexes. Okay, some of the indexes are selective, and you also have unselective indexes as well in your environment. So you are performing DML on multiple instances. Okay, if that is the case, what will happen? In addition to a data block, your index blocks also must be updated and modified as a part of a DML. So I'm giving you one example. Let's say as a part of a DML, we also modify index block from instance 1, for example. We are connecting to instance 1. From instance 1, we actually make some changes on this block. And also, the before image is saved in here. Okay? That's one thing what we can see. Another one is, so now we have another request from here. From second instance, and we also request the same block for another DML in the same block. So in this case, what we need is this. So we have a same block here. And also, I want to make another change here. So in order to make another change, what do I need? I need actually block from undo table space. So in this case, let's say I do have undo block copied. Actually, this got to be red color. I will change the color. So we have undo block from this undo table space, and then we copied before image because we are making another change here. And also, we have another DML from instance 3. So in that case, this block is copied over here. And also, maybe this one. And undo table space, undo block is also copied to keep before image. So in the first time here, in this case, we made one transaction, but before the commit, another instance requested same block to make another transaction. So we have another transaction. So we have 2 uncommitted transactions here. And also third instance also requested the same block before the commit. So in this block, now we have changes from 3 instances. And before image is stored in this undo block, before image is stored in this undo block, before image is stored in this undo block. Now, at this time, I have a session from ORCL4. I need a reporting query. So I need a full table scan. So these are all before the commit. So what do I need? I have to create consistent reader block. How? Can I just copy this block? Just copy this block to create consistent reader block? Because I can apply the undo data directly to copy the block. Can I create consistent read block? No. Why? Because this include changes from this instance, changes from first instance as well. So I have to apply more changes, more actual undo. So where is my undo? I have undo that stores before image of a transaction 1. I have another undo here that saves before image of the transaction 2. I need all this information here, so I have to apply all these undos finally to create consistent read block, and I can get that information. If this were a real environment, okay, I modified many number of table blocks. Because of that, you have 10 indexes must be modified. That means there will be multiple the undo blocks are generated because of your table changes, and that will cause another index block modification. If you need to actually read the consistency as a part of full table scan, then we have to copy undo block from all of the places to provide the consistency. So this will be one challenge. So in this example, the possibly drop unused, unselectable indexes, and also you can also commit your transaction timely manner instead of leaving uncommitted transaction for a long time. Okay, and this example is because you made a transaction but you haven't committed. Because of that, we had to copy excessive number of undo blocks, okay, through the interconnect. That was a problem. So let's come back here. So let's get into next page. And also we have a high watermark consideration. And think about that. Your environment is a data warehousing environment. But your the extent size is too small. For example, you created a table space with auto-allocate extent management and extent allocation. And initial size of extent is 64 kilobytes. But this is data warehousing environment. If that is the case, whenever you perform ETL load, you need a large amount of space, but each time when segment is filled up, we have to allocate 64K at the extent level. So because of that, we will have to adjust high watermark frequently. That will actually there will be the one bottleneck area. So you may see high watermark contention related the wait event, or global cache current related wait event. So how can I resolve this problem? One possible the option is, if this were in a data warehousing environment, if you are expecting concurrent insert statement or bulk update, bulk insert statement, then why don't you use the bigger size of ASM, the bigger size of extent. If you are using uniform extent size allocation, then maybe you start with a 4 megabytes or 1 megabyte. If you are using auto-allocate extent management, then you may want to change the initial extent size something greater than 1 megabyte or 4 megabytes. By doing so, every time when space is needed, you allocate large enough space, and then we have enough time to fill that extent. And the next time when we need additional space, then we allocate another extent, and then we can adjust the high watermark. So that's what we can use. Another one is concurrent cross-instance call consideration. Now this is related to drop and truncate. In RAC environment, when you issue truncate, it does require object and table level checkpoint. So, to do so, when you issue truncate command, and there will be the cross instance call to identify dirty blocks across instances, and then flush those dirty blocks to disk as a part of an object level checkpoint or table level checkpoint. Now, if you have a multiple truncate across multiple instances, then what will happen? Only truncate command is served one at a time. So if you have a first truncate command, then second truncate command must wait until first truncate is complete. And that may cause another point of serialization issue. So that's another consideration. What if you have a concurrent truncate and you also have a parallel query running? Meaning that I'm issuing parallel query that requires direct I/O. I'm doing direct I/O, so I need a consistent image of data, but my dirty blocks in memory, and you'd also have a concurrent truncate command. The concurrent truncate command, it must wait for previous truncate command to complete. And so we have to wait the time because truncate command manages it serially, and you have a direct path operation like a parallel query that requires checkpoint to read the dirty blocks. So you may have this kind of concurrency scenario. So it's a good idea to handle this concurrent truncate and other operations properly. So you have to know concurrent truncate requires cross-instance call. That's one thing what you have to know. So serial truncate command management. And another thing is the truncate command requires segment and the object level and table level checkpoint. Thus, they may affect other parallel queries as well. So in order to resolve this, maybe you can actually, instead of spreading blocks of a segment, blocks of object across instances, you may want to actually limit where the blocks can spread. So you can create, if you have a very large table, you may want to create partition table. So by doing so, we can assign ownership of blocks of object to specific instance. So by doing so, your instance call can be handled faster. So this is one of the considerations in RAC environment. So this was the second part. I briefly introduced tuning tips.